Today, he will discuss nano-engineered surfaces for enhanced condensation in energy applications.
Thank you. Thank you so much for the nice introduction. Good afternoon, everyone. Thank you, Arvind, for the invitation. This is an amazing workshop. I'll talk today about nano-engineered surfaces relevant to condensation. So switching gears a bit from boiling to condensation. Before going into that, quick brief about what we work on. So we work on the intersection of mechanical, chemical, and materials engineering, looking into surface modification, surface engineering for a lot of applications, thermofluid applications, drop impacts, as well as definitely phase change heat transfer. We start from, let's say, a very basic structuring of surfaces or modification of surfaces. I'll come across, what we focus on are scalable methods which can be scaled up from lab scale to, let's say, industry based heat exchangers, to the fundamental physics in terms of the condensation, as well as the overall, the efficiency or the gain that we are getting in terms of the heat transfer or water harvesting. So the primary motivation behind most of our work comes from nature, as is most of the things or most of the engineering designs. We try to understand the nature's design, be it the lotus leaf, be it the Namib desert beetle, be it the water strider, and we try to mimic that to develop surfaces that can be relevant in across a lot of applications, including condensation. Condensation, as you might be aware, and this is something that need not be told to this audience, we have starting from power generation, HVACR, desalination, the more conventional applications, to the more recent electronics cooling, battery thermal management, as well as atmospheric water harvesting, which all require or involve condensation. Now, before we go into the different kind of surfaces, before we look into that, let's just quickly go over surface wettability. Yes, this has been covered, so I won't take too much of time in it. The way we define a surface as a philic or phobic is based on the contact angle. So if the contact angle, which is the angle that a liquid droplet makes with a surface, if that angle is less than 90, it is philic. If it is greater than 90, it's phobic. And then we have the two extremes, which is the superhydrophilic and the superhydrophobic. And depending on the application, we may choose to have a wettable or a superhydrophilic surface, or we may choose to have a hydrophobic or a non-wettable or a superhydrophobic surface. In terms of how the structures play a role when a droplet sits on the surface, so we can have what we call as a Wenzel model, in which on a structured surface, the liquid penetrates and fills the gaps within the surface, or we can have more or less a leviated or a floating droplet, which is a Cassie-Baxter state, wherein between the structures you have the air filling in the gaps and cushioning the droplet, which is what is we invariably have for a superhydrophobic surface. Now, on the other side, when we talk about condensation, when a vapor condenses on a surface, it can either condense to form a continuous film, which is the film-wise condensation, or the surface can be such that it forms discrete droplets, and before the droplets can coalesce and form a film, they are removed by gravity or other forces, which is the drop-wise condensation. And it has been shown over the years that drop-wise condensation can have 5 to 7 times higher heat transfer rates or heat transfer coefficients. So connecting the two, what we have is primarily in a wettable surface, a hydrophilic or a superhydrophilic surface, we are expected to find film-wise condensation. I will contradict this very statement towards the end of the presentation, but for now, on a superhydrophilic or a hydrophilic surface, it is expected to find film-wise condensation, whereas on a hydrophobic or more on a superhydrophobic surface, we are expected to get drop-wise condensation. So then the question comes in, how can we have a hydrophobic or a superhydrophobic surface? Or in other words, how can we come up with engineered surfaces that can promote drop-wise condensation? So to give you a brief outline of what we'll cover, I'll start briefly about the different micron and nano-engineered surfaces that we can have, which can be helpful for enhanced condensation. I talk about a little bit more in depth about special type of condensation, which is jumping droplet condensation, where two droplets coalesce on these kind of superhydrophobic surfaces, allowing them to jump off the surface, thereby enhancing condensation. I will talk a bit about my postdoctoral work, which is condensation of low surface tension fluids on specially designed lubricant infused surfaces, as well as durability of enhanced surfaces. I think there were a couple of questions in the previous talks where the durability, came into the picture, and it was a good question as to, how durable are these surfaces. And finally, I'll talk about dropwise condensation on smooth surfaces or surfaces which are inherently filling. So to begin with, on micro and nano engineered surfaces, what we have is, across over the years with the advancement of fabrication, with the advancement of different methodologies, there can be a wide range of structured surfaces that can be developed. We can have silicon micropillars, which are very organized, which have very high thermal conductivity, but at the same time, they are expensive and they are not really scalable to a standard where we're looking for industrial applications. Similarly, we can have gold nanowires, we can have CNTs, excellent thermal conductivity properties, ideal for heat transfer surfaces. However, these again are expensive and are maybe not as scalable compared to metal oxides as well as a metal deposition, something that Professor Arvind also covered earlier today. These are very easily, through chemical etching, they can be fabricated. So therefore, they are highly scalable, as well as there is not much compromise on the thermal conductivity, given the fact that these are very thin layers or very thin coatings. In fact, if we can have metal deposition, let's say for copper, then we maintain the thermal conductivity, as well as we can have scalable and different length scales. We can also have hierarchical structures in which we are mixing different, for example, we can have laser texturing along with chemical oxidation, and we can have very definite structured or a textured surface, which are the hierarchical surfaces. So in terms of the fabrication, if we look at metal oxide, this is very similar to what Professor Arvind covered before. This is for copper, or even for aluminum, where copper we have an alkaline solution in a temperature bath of 95 degrees C, or if it's aluminum, even in a DI water or deionized water at 90 degrees C, we end up getting very fine structures. On the bottom, you see the structures of copper oxide, which are knife-like or edge-like structures. On the right, you see bohemite structures, which are on aluminum. So the top right, which have a length scale of about 1 micron. So these are definitely something that are very scalable or easily doable, surface structuring that would make the surface super hydrophilic or hydrophilic. Once we have the surface structure, once we have a rough surface, we can then go on to functionalize it with a hydrophobic. In this case, we're using HTMS, which is a form of a silane. It's a chemical vapor deposition, a very small 5% by volume in toluene, a very small volume of the solution in an enclosed container along with the surfaces is going to uniformly coat the surface with the silane molecule or the phobic molecule, making these surfaces super hydrophobic. Now, in terms of the scalability, this is something that we have done, not just limited to, let's say, flat plates or small plates or tubes. We have actually coated entire fin and tube heat exchangers, aluminum fin copper tube heat exchangers. Simply, we scale it up. Instead of using a small container, we now have a drum, let's say in case of aluminum, filled with water, boiling water, and we can structure the fin surfaces of these heat exchangers. And then in a similar drum, we can have vapor deposition, which would render them super hydrophobic. So the advantage or the utility of this method is that we can scale it up from from a very small scale or lab scale surfaces to a higher surface, to a higher length scales, which can be of the order of 1 meter. There's also, beyond chemical functionalization, we can also have electrochemical etching, in which case what we are looking at over here are different grades of aluminum. And in electrochemical etching, depending on the time, depending on the grade of aluminum, we will end up with different structures. Yes, these will not be nanoscale structures, these will be microscale structures, but couple these with the chemical oxidation, we can now have a hierarchical structures which are micro nano structure. And these are again very scalable, uncontrolled but scalable surface structures that can be developed. Of course, the different features or the roughness is going to be a function of the time of etching in this case for electrochemical etching. We can also have the other way. In case of electrochemical etching, we are removing material. We can have deposition, cathodic deposition of the metal. What you're seeing over here are copper surfaces. So depending on, as you can see, depending on the time of deposition, the structure length scale would change. The depth of these grooves will also change. But this is also something which can be utilized to have a controlled structure over a larger area. It is worth mentioning that this will need, or these kind of surface structuring does need post treatment, which means either through higher temperature annealing or some other treatment is usually necessary. Otherwise, with time, the deposited particles can be flaky, and with when we have, let's say, a condensation application, these may start degrading, these surfaces may start degrading. So as I was mentioning, in case of hierarchical structures, we can have a very well defined, so we can use laser texturing initially to define macro scale or micro scale bumps. And on that, we can then do chemical oxidation, we can do functionalization, or we can do electrodeposition to end up getting very defined nanowire structures. And what it allows is, and this is not something that I will go in depth today, but what you can get the idea that based on the particular application, you can control the structuring, or you can control what kind of surface features you would want. So those parameters can be, let's say, your droplet diameter, those can be your, let's say, the temperature difference or the temperature gradient you want. You can control these structural length scales. Now, just to give you an idea of how these help. So essentially, when you have different kind of structures, you can have a Wenzel state, you can have a Cassie-Waxter state, you can also have a partial wetting state, and therefore, in terms of dropwise condensation, what ends up is you end up getting much higher heat flux or much higher heat transfer coefficient as compared to a traditional, let's say, metal surface, copper or aluminum surface, which would inherently have film-wise condensation, and therefore these surfaces are desired to have higher heat flux or higher heat transfer coefficients. Now, moving forward to a specific kind of condensation, which is the jumping droplet condensation, and this stems from the fact that back in 2010, Morieko and Chen identified that when two droplets coalesce on a superhydrophobic surface, there is an excess of surface energy, right? Because when two droplets are coalescing, your total surface area is going down. Therefore, you have an excess of surface energy, and then that can help in propelling or bouncing the droplet out of the surface. So what you see over here is essentially two droplets coalescing and jumping. And in a condensing scenario, when you have number of droplets condensing or number of condensed droplets, when they are coalescing and jumping out, it is essentially regenerating the nucleation sites for fresh vapor to condense. So this is an additional method other than gravity removing the droplets, an additional method which is going to help in removing condensate droplets from the surface. Moreover, this is, in both the cases, gravity is acting downwards. Moreover, this is against gravity, which means that I can have out of plane, in the opposite direction of gravity, droplets jumping and helping in cleaning the condenser surface. In terms of the applications, then some of the applications that we were looking at before in terms of heat pipes or in terms of vapor chambers. So in this case, what you find is on a superhydrophobic copper oxide, what you see as those parts, those are jumping droplets, and they can have a wide range of applications. In particular, this is a work from a while back in 2013 by Professor Milkovich. What we find over here is, compared to dropwise, in case of jumping droplets, your departure droplet diameter is much smaller, and therefore you end up getting much higher heat transfer coefficients even compared to dropwise condensation. Of course, there are limitations to it. There's a limit. This is not realizable at every condition. This is realizable at a given vapor pressure, but in the range when it is realizable, it does end up giving much higher heat transfer coefficients. One of the applications of this can be in case of in case of electronics cooling, where what we have is essentially, if I have a cold superhydrophobic surface which is actually in the downward direction, then you could still have the droplets, because of jumping droplets leaving the surface against gravity and going back and hitting the hotspots on your electronic component or the GaN transistors. So such can be the applications of jumping droplets. Yes, there's a lot of let's say debate about how efficient this system is, or this method is, and to what extent is the cooling going to be enhanced in a complex system. But nevertheless, this is a mechanism that can help in enhancing dropwise condensation. Now, in another form of enhancement of a condensation on superhydrophobic surfaces can be in the form of what we call as hierarchical condensation. What happens is on a superhydrophobic surface, because of the surface roughness, as the condensate droplet grows, if you remember the Cassie-Baxter state, the droplet pretty much sits on top of this, cushioned by air within the micro gaps or within the microstructures. Now, in a condensing scenario, when you have the surface colder than your outside vapor, you can also end up getting nucleating droplets within the surface structures, very small tiny droplets. Now, once you have these droplets over here condensed within the microstructures, what happens is they are getting sucked in by the larger droplet, which means that your larger droplet is acting as a sink to these smaller micro droplets which are condensing within the structures, and therefore your droplet growth rate can increase. In case of a hierarchical condensation, the faster the droplet grows, the faster it will be removed by gravity, and therefore faster can be your heat transfer performance or your heat transfer efficiency. So it can follow basically a chain. You have a nucleation and growth beneath your largest sink droplet, followed by the coalescence with the sink droplet. You have again a renucleation in these microstructures leading to the growth, and therefore you have a continuous coalescence with the sink droplet and the droplet growing. So this can be also a mechanism through which the condensation can be enhanced, which is through the hierarchical condensation. Now, moving on to the condensation of low surface tension fluids. When we talk about hydrophobic or a super hydrophobic surface, we are talking about it being non-wettable with water. Relatively, it is easy to develop a super hydrophobic surface because water has a very high surface tension of 72 millinewtons per meter. Comparatively, your surface, if it is in the range of 19 or 20 millinewton per meter, you would end up getting a super hydrophobic surface. However, the challenge becomes when we are not dealing with, let's say, water, but we are dealing with low surface tension fluids. In the low surface tension fluids, even a super hydrophobic surface or a hydrophobic surface, for example with ethanol or hexane, would become super hydrophilic because of the low difference in the surface tensions. So therefore, the question comes in that how can we come up, or the question was, how can we promote dropwise condensation of these low surface tension fluids? Because on a super hydrophobic surface, ethanol would condense in a film-wise mode. So, inspired by the pitcher plant in nature, what the pitcher plant has is in its outer rim, the pitcher of the pitcher plant has a wax, kind of a liquid infused. It's a carnivorous plant. So, when an insect pretty much sits on that outer rim, it slips because of the wax and falls inside and meets its death. So, inspired by the pitcher plant, back in 2011, Professor Eisenberg's group at Harvard came up with liquid or the lubricant infused surfaces. It is essentially a porous surface. It can be any surface with sufficient porosity, and then you have a liquid or a lubricant which is infused, can be through dip coating, can be through spin coating, which stays or is confined within this porous structure because of the capillary forces. So what this leads to is the fact that now, instead of having an external foreign liquid droplet with a solid interacting, we have a liquid-liquid interaction. And once we have a liquid-liquid interaction, what gives us is, it gives us ultra-low contact angle hysteresis. If you remember from the earlier talk that Professor Arvind mentioned, you had contact angle hysteresis as the difference between advancing and the receding contact angle. And in this case, because you have a liquid-liquid interaction, you have much lower contact angle hysteresis. And that helps in the fact that if you look at the contact angle hysteresis as a function of surface tension, for water, both are quite comparable, super hydrophobic surface as well as low surface tension fluids. But as the surface tension of the fluid goes down, what we find is this being that of super hydrophobic surface, the blue dots, the liquid infused surfaces or the lubricant infused surfaces show much lower contact angle hysteresis. However, it comes with its own demerits, it comes with its own challenges. The first and foremost is it has to be a lubricant or a infused liquid which is immiscible with the foreign fluid, or in this case with the condensate. There's also a term which we call as lubricant cloaking, which is essentially if I have an external droplet, let's say a water droplet sitting on the surface, and I have an oil layer on the surface, the oil layer can encapsulate or cover that water droplet. Right, so that is termed as lubricant cloaking. So we don't want lubricant cloaking because that is going to prevent the interaction of vapor with the liquid, as well as there can be shear drainage. Of course, we have a liquid, so if we have droplets, depending on how well the oil is infused and the different forces acting, we can end up having shear drainage, which is also something which we do not want. So in terms of fabrication, this is and this particular shape of the condenser tube was done because of the setup that we had. The same as we were doing before, we had a chemical oxidation to have initially the structures. Then we functionalized the surface to make it super hydrophobic, and then finally through dip coating we ended up getting the liquid infused surfaces or the lubricant infused surfaces. As you can see, for water, whereas a super hydrophobic has a contact angle of 165, in this case for liquid infused surfaces the contact angle is actually lower, it is about 120 degree. However, before going into that, we did try a lot of different lubricants or infusing oils. So Crytox and Formlin, what you see over here, are proprietary name of perfluorinated oils. So basically there are you can see the structure over here. Whereas we also tried different viscosity of silicon oils as well as mineral oil and ionic oil as different lubricants that can be preferred. In terms of the contact angle, what you find over here is, so we were looking at hydrophobic and super hydrophobic, which fails with ethanol and hexane. But now when we look at the lubricant infused surfaces, you see fluorinated oil over here and silicon oil infused surface over here. You find that these, yes, they are not phobic, but nevertheless they do have a finite contact angle, and maybe this will help us along with the ultra low contact angle hysteresis in giving us or promoting dropwise condensation. So in other words, for lower surface tension fluids, it does appear that liquid infused surfaces can be more relevant than a super hydrophobic surface. This is just the facility we had at UIUC. I won't go too much into the details. This is the condensation chamber. We're doing a pure vapor condensation. The tube sample that you saw goes inside the chamber. It goes to a pressure of about, or initially it is pumped down with the vacuum pump to a pressure of about 0.1 pascals before the secondary boiler supplies the vapor into the chamber. So the chamber is filled with the vapor of be it ethanol, hexane, or water vapor or steam, and it condenses as external condensation on the external surface of the tube. The tube is connected to a recirculating chiller which is controlling the temperature of the cold fluid which is flowing. So looking at the mode of condensation before looking into the heat transfer, what we find is on a regular hydrophobic copper. The reason why we chose hydrophobic copper is because it has a comparable angle, contact angle as for water as compared to a lubricant infused surface. And what we find is, as expected, for steam it does show dropwise, but for ethanol, hexane, and pentane it shows film-wise condensation. Whereas in case of the Crytox infused LIS or liquid infused surfaces, we find that we get very robust dropwise condensation for these fluids. In terms of the heat transfer coefficient, what we have over here is because of the rigorous dropwise condensation, and keep in mind that over here the contact angle is actually less than 90 degree. We have about 65 or 70 degree contact angle, yet we get dropwise condensation because of the continuous removal of the condensate droplets, in this case ethanol, or the ethanol droplets slip on the surface, and because of that we end up getting a heat transfer coefficient which is about 3 times higher as compared to that on a hydrophobic or a super hydrophobic surface where we realize film-wise condensation. The large error bars over here is primarily because we had a 30 centimeter long tube, and it is maintaining the saturation pressure at let's say a given fixed value for ethanol or for hexane, given its volatility was not very easy. That ended up giving us a fluctuation in the heat transfer measurement, and therefore the large error bars. Nevertheless, it is evident that drop-wise has much higher heat transfer compared to film-wise. When we further go down in terms of the surface tension of the fluid for hexane, which has a contact angle of about 35-40 degrees with the slip surfaces, we still end up getting drop-wise condensation. Yes, maybe not as robust as what we see for ethanol. You can see larger puddles or pools being formed intermittently, but then these are removed by gravity, and what we end up getting here too is a higher heat transfer coefficient for drop wise as expected as compared to the film wise condensation. Now, the major challenge or the major limitation of accepting or these lubricant infused surfaces being accepted in an industrial application is the fact that what is the durability of these surfaces. So we did a bunch of durability tests. We started with the thermogravimetric analysis test, which basically what we did is we collected the condensate and then we did a TGA. TGA is essentially heating up the solution or the fluid at regular temperature intervals. And what we found over here is, so if there is any lubricant in or that is being lost from the condenser tube, it will be collected in the condensate, and therefore we should have seen a peak or we should see a presence of the lubricant, but we did not see significant or we did not see any traces of the lubricant in the collected condensate. We further went and did 2D GC to get to understand what is the extent of lubricant drainage, because of course there has to be some drainage even if it is in the range of ppm or ppb. And what we found is, based on the lubricant or based on what we are quantifying through a GC, we then predicted the lifetime of these LISs for different heat fluxes. And what we find is these are sufficiently robust. We are looking at in general a 1 watt per centimeter square in case of ethanol or hexane condensation, and that would end up having at least for ethanol considerable lifetime, which is something that would be beneficial in terms of enhancing heat transfer. This is also something that was done in collaboration with British Petroleum, and they are currently testing these surfaces in their pilot plants, and hopefully these are robust enough to be implemented on an industrial scale. We did some of the durability tests on our own, where what we had is in a chamber we ran condensation in a closed loop. These are with steam, these are not with ethanol, but what we find is over a period of, here we're looking at 60 days, what we have is even for longer time periods, what we find is that these surfaces are sufficiently durable. There is not much lubricant lost because the lubricant is held together by the capillary forces, and it just retain the drop-wise condensation. Moving on, looking into the durability of the enhanced surfaces, this is something that is always a question as to, be it the superhydrophobic surfaces or the lubricant infused surfaces, how durable are these surfaces? And what you can see over here is, this is basically a coated surface. And once you have vapor condensing, you can see these marks over here, which shows that the coating has delaminated, whether through a pinhole or through other methods of delamination. It's a Teflon coating, and then the vapor has seeped into, and therefore leading to breakdown of these surfaces. And if we think of the surface failing from let's say hydrophobic to, let's say, hydrophilic or superhydrophobic to less wettable surface, what that means is we are now coming down from drop-wise condensation straight to film-wise condensation, and this order of time or the order of magnitude of time can be very small. And what we are driven towards is first to understand the cause of this degradation, and secondly, what can we do to enhance the durability of these surfaces. Now, on one hand, what we have is, it can be that the coating is, or the surface, the engineered surface, the structures are getting eroded. That is the cause of the failure or the cause why the wettability is lost. However, in most cases, possibly it is not the surface that is degrading, it is the absorption of either some molecules or contaminants which is creating this degradation on the surface. What we are seeing over here is condensation on a surface, where what we find is initially the surface is pristine clean, and then as we keep repeating the cycles, we start seeing at very random locations, we start seeing specks. And what we find is beyond a certain, let's say, and this is of course a function of this particular experiment, but beyond a certain number of cycles, now we have actually defined in a way the nucleation sites, because after this, on the 101st cycle, the droplets are going to nucleate exactly where the specks are. And this was very interesting. This was something that was seen without, not because we wanted to or we are looking for it, but quite randomly when doing the condensation experiments, we started seeing that the surface is degrading over a period of time when we do condensation experiments. And what that led to is looking into, so these are AFM images and SEM images as to what exactly is happening at those locations where we are seeing, these specks, at least through the microscope. And what we find is that there are some deposition of some kind of formation or a deposition that has happened at those locations. And as the number of cycles increase, what we find is this deposition, let's say the volume of this deposition is also increasing. And likewise, the volume increasing with the number of cycles. The number of cycles represents the number of cycles of condensation. So we started looking into what could be the reason for this. And for this, what we did is we did experiments at different locations. So for example, one set of experiments was done at Illinois in US, which is relatively less industrious in the sense that it was in Urbana-Champaign. Another set was done in China, in Tsinghua University. And what we found is this rate of agglomeration, or this rate of increase in volume of the contaminant, is a function of the place, not just a function of the number of condensation cycles or number of cycles. And what we hypothesize is it comes from the volatile organic compounds, which is all around, and that leads to different VOCs which get absorbed on the surface, and once it gets absorbed, it then self-assembles to form a deposition on the surface. So what we have is, if we have a condensate, and then as it evaporates, when we're cycling between different cycles of condensation, the liquid is evaporating. When it is evaporating, it is kind of allowing those molecules to kind of come together and form an agglomeration in the form of and leading to a deposition. Now, to further validate this, what we tried is we started with a bare copper, a pristine bare copper with plasma clean, which we clean through plasma. And what that gave us is initially so at time equal to 0, we got a super hydrophilic surface. We left the surface just in a lab environment, not in a completely airtight container, but let's say in an open petri dish. We left it in the lab environment, and what we found is, with respect to time, with respect to number of days, the wettability of the surface increases. Now, we utilize this to come up with structures in such a way that beyond a certain point, let's say beyond 20 days over here, a surface would become super hydrophobic pretty much on its own. So by absorption of the volatile organic compounds, along with the structure design, we ended up pretty much having a wettable surface become a super hydrophobic surface over a period of time. And what you can see over here is these are the different, let's say, conditions. We have plasma clean, we have lab environment, as well as we have in a sealed environment. What we find is, it's basically a function of the adsorption of these molecules. So coming to the last part of the talk, I started the talk with the fact that dropwise condensation is something that is realizable in non-wetting surfaces. And we said that we need a super hydrophobic or a hydrophobic surface. And why is it so? Because one of the major challenges is we need to remove the condensate. On a hydrophobic or a super hydrophobic surface, we can remove the condensate before they coalesce and form a film. And therefore, higher the contact angle of water on the surface, easier the condensate droplet departure. However, if we think from the perspective of nucleation of vapor on a solid substrate, the work needed for nucleus formation is a function of the contact angle, and what it shows over here is smaller the contact angle, lower is the activation energy or the nucleation energy barrier for condensation, and therefore purely from a nucleation perspective, we would want essentially a surface which is hydrophilic, which means that the wettability that promotes nucleation is hydrophilic, whereas the wettability that promotes enhanced condensation turns out to be hydrophobic. Then the question is it that only non-wettable surfaces alone that can promote dropwise condensation? And the answer is actually no, because what we have is, if we have wettable surfaces in which we can by some mechanism be able to remove the droplets or the condensate before they can coalesce and form a film, we can still end up getting dropwise condensation, which means that we need a surface which has ultra low contact angle hysteresis, at least theoretically, which has a contact angle hysteresis close to zero. So therefore, the moment the vapor nucleates to form droplets, it is removed from the surface even before it can coalesce with the neighboring droplets. And in fact, this is what we found is most of the surfaces that is fabricated either have, if they have a very high contact angle, they also have low contact angle hysteresis. And surfaces which have low contact angle actually also end up having high contact angle hysteresis. So it is hard to fabricate or develop or come up with a surface which is philic, which is having a low contact angle, at the same time having low contact angle hysteresis. And of course, those are very valid reasons, because you have the surface roughness, you'll have a larger droplet and the surface interaction, so therefore it's very difficult to get low contact angle hysteresis. However, if you think of the liquid infused surfaces that we just talked about, with ethanol and hexane, both of them have contact angles which is less than 90 degrees, sufficiently less, and yet they are robust enough to show dropwise condensation. Same with some of the, let's say, commercially available coatings. We don't know too much about the details of the coatings, but they can again promote dropwise condensation even when the contact angle is low. Some of these methods, these are the works out there in the literature where they do different kind of surfaces, something called the slippery covalently attached liquid surfaces, SoCal. There can be also pegylated surfaces. These are all grafting polymers onto the surfaces in such a way that while you have a lower contact angle, but you also have lower contact angle hysteresis, as you can see over here for a blood stain, and these can or has the potential to promote dropwise condensation. So with that, on the concluding slide, I would just like to highlight, that the condensation is there anywhere and everywhere. You look around, there can be different applications of it, starting from thermal management, water, energy systems, which we have focused here, manufacturing, as well as a lot of, let's say, the durable coatings, which is something of interest, that has always been of interest. The question still persists that after probably 80 to 100 years of research, we still don't have a surface robust enough to sustain dropwise condensation over long periods of time, as well as a lot of these surfaces also have added advantage of antibacterial as well as antiviral, which is something of relevance when we are talking about micro and nano engineered surfaces. So with that, I'd like to thank you all for your patience, and I'll be happy to take any questions.
That those feed back into the main droplet. I mean, is that always the case, or is that going to depend on your surface and their droplet sizes and so on, and the shape of the structure?
Yes, that is a very good question. Yes, indeed, it's not that it will always happen. It depends a lot on the first of all the degree of subcooling that we have, as well as the structure length scales. Because on one end we can have hierarchical condensation, on the other end we can also have transition to Wenzel state. So if the structured or the droplets inside the structures are growing fast enough, they will coalesce and they'll form a film, and it will transition to a Wenzel state. So yes, that is one of the mechanism, but definitely not always realizable. This is on a special case when we can have hierarchical condensation. It's very true.
So is there some sort of a general method for looking at this, or when this happens or not? And the reason I ask is because we spent a lot of time making super hydrophobic ceramic surfaces, except we would always end up in a situation where after a couple of days that thing would be flooded. and then you have to go back and put it into a vacuum, and it would regenerate. But we could never get it to stay hydrophobic.
Right. That's a great question, Professor. So, in terms of the conditions, there can be or there are regimes where, let's say, in a particular degree of subcooling, particular saturation pressure, we will get one form as opposed to the other. But in most applications, that is not in our control. As a thermal engineer, we don't get to control, the vapor or the conditions, and therefore we have to rely on the surface. Uh, there is still no definite answer to like this is going to definitely be able to sustain the dropwise mode or is going to sustain stability, which is something that is to look into in depth as to what we can do in order to sustain the surface wettability.
You can go ahead.
Okay, fine. For the lubricant impregnated surface, so you did the gravimetric analysis of the liquid that was collected. But if you look at just the condensation heat transfer over days, how does it behave?
Yeah, so the heat transfer did not degrade over a period of close to 7 months. And the reason why it ended up with 7 months is so this was back in UIUC. We were testing, and then there was an outbreak of COVID. So everything was shut down, and we went home, and the experiment kept on running on its own. And when we came back after 6 or 7 months, it was still showing dropwise condensation. So we took and we did the measurement of the heat transfer coefficient. So there was no degradation of the heat transfer coefficient. But then the question did remain that there can still be some depletion or some loss of lubricant. That is where we went back to the TGA and the JC.
Hexane and the other fluid.
This is with ethanol and hexane.
But with water, will you
With
say
water, the surfaces are not, yes. And that's a very good question. We believe that with water being a cloaking fluid, what we have is the oil cloaking the water droplet leads to faster depletion. And therefore, for water, it was about 45 days, 42 to 45 days where we had the dropwise condensation. So these surfaces are more robust with ethanol or hexane than they are with water.
Last question is like you showed that if you make a surface super hydrophilic and leave it, the contact angle keeps on increasing. Do you have a method of how to keep it super hydrophilic?
So that's a very interesting question. We generally try to keep it submerged in water, right after fabrication. It is not foolproof, but it does keep the superhydrophilicity for a longer time as compared to exposed in the air. It can also be, of course, in a vacuum kind of a chamber, a desiccator, or so forth, but it might be very cumbersome in a way to handle such samples. But keeping it submerged will keep it superhydrophilic for a while.
Because since it's a metallic surface, the contact angle actually changes in situ while working on these condensation or during boiling applications
True.
or so on.
True, and that leads to the fact of
Changes
the wettability. Yes, yes.
So from participant side, anyone wants to ask?
So,
Yeah, please.
so a basic question, okay? Like when you are having these type of structures, which are having air in between, so it appears like we are having a layer of material which is having higher resistance. And as you increase the height of the structures, this resistance will go on increasing. So, is there optimum? Is there anything I'm missing? And is there any optimum height on which this
No,
works?
you're absolutely right. The fact that you have air as a very poor thermal conductivity. So the fact that there's an additional layer of air which is adding on to the thermal resistance. But I think the fact over here is that these are so thin. We're talking about, let's say, 2 microns or 1 micron or 500 nanometer thick surfaces that does not contribute significantly when I'm comparing with the heat transfer enhancement that I'm getting through dropwise condensation. So yes, of course, there is some increase in the thermal resistance because of or decrease in the thermal conductivity. But in the bigger scheme of things, that becomes a very small percentage as compared to the enhancement that I'm getting. And yes, you're right. The taller we have the structures, more will be my thermal resistance. Yes.
So I have a question regarding the lubricant infused
Yeah.
surfaces. So rather than making a super hydrophilic surface and then treating it with the lubricant, I can't take any material which is a porous material of known porosity and then impregnate the lubricant and then see how it changes with the function of porosity and permeability, whether there is a qualitative and quantitative difference in
We
the.
can do that. We can do that, and there are some works out there who do with, let's say, electrospun nanofibers.
Because the contact angles that you showed are
Yeah.
with a particular type of super hydrophilic surface, right?
Yes.
But now, if you change the porosity of these, nanopores or whatever that you have, and then you vary these as parameters and check the lubricant impregnation. So then, how do you see the actual changes in the contact angle as a function of these parameters, these porosity parameters, for example?
Yes. So yes, that's a good point. So in that case, it has to be a function of, let's say, the volume of lubricant that we are infusing, and whether it leaches out from the porous surfaces with respect to time, as well as for most porous surfaces, it could be a film wise, or it could be the condensate actually going into the porous, like a porous surface condensation, and then the metrics will be different in that case, to be able to quantify the whether there's an enhancement or not in terms of the porous surfaces.
The reason why I'm asking is if people wants to replicate this kind of surface, so the nature of etching is process can be different. Somebody can etch it more, somebody can etch it less. Then the contact angle can completely become different. Whereas if you quantify in terms of porosity and of the structure, fixed porosity, fixed material,
Structure, okay.
maybe there is more chances that you can replicate these
That
kind
with
of.
a different material or
Yeah.
even different. That's a good suggestion. Sure.
Whether these are vacuum compatible, these surfaces. Means if I in space if I want to use whether
So
is there any degassing issues?
So the lubricant that we use over here, the Crytox, that is actually the vacuum grade liquid or a vacuum grade lubricant. However, given that these are held together within the surface by capillary forces, so depending on the level of vacuum, so we go down to about 0.1 Pascal. It is very stable to that pressure.
That is high because if we go to
That is high for space applications.
space application,
Yes.
it is
So, like, it's something interesting and might be, good to explore to see how, these are compatible at ultra low.
yeah.
So we have done, for example, scanning electron microscopy of these surfaces, and the lubricant still stays, but we have not done a very well characterized, let's say, pressure based or vacuum based calibration or looking into the wettability.
Yeah, two more questions.
Small question. So all these studies you have shown, if I not missed anything, that it is for the vapor state is scanning zone. It is not full. But most of the industrial application, when it is for space vacuum application or semiconductor application, then there would be some flow, and sometimes this flow is quite high. So how this surface will be effective there? Because sometimes we don't want condensation to happen.
Right. So that's a good question. We do not have an entirely static vapor. We do have a vapor that is coming in from the boiler, but I do agree with you that the velocity of the incoming vapor is not affecting the condensation. Whereas I think what you are referring to is a condition where you have a vapor with a significant velocity. So these kind of surfaces are to enhance condensation, whereas there can be an opposite end which is to inhibit condensation. And right, and we were working with a blue star, which is we wanted exactly the same thing on a glass panel. They don't want condensation to happen because then you lose the transparency.
But then it's still stagnant.
That is still stagnant. Yes. So depending on the vapor velocity, we can look into it and we can think about what could be probably a direction to pursue.
Nice, William. So you have mentioned water harvesting, dew harvesting as one of the application. So can you comment on the effect of wettability on dew harvesting? Which wettable surfaces is more preferable for dew harvesting?
So dew harvesting is same as condensation, right? So in case of a dew harvesting, the experiments that I showed over here are in pure vapor. In a pure vapor for dew harvesting, of course there won't be dew, but in case of water harvesting, it is going to be a super hydrophobic surface. But in case of, let's say, atmospheric dew, you have the non-condensable gases, and I think Professor Arvind was also covering earlier today. In the presence of non-condensable gases, the dynamics can be very different, and Professor Pallav works in the same direction, where what we find is it's not necessarily that a non-wettable or a superhydrophobic surface would be the best. It may so happen that a film-wise condensation on a superhydrophilic surface is your better bet in a dew harvesting. Also depends on the conditions. If your degree of subcooling is significantly large, then a non-wettable surface still might be better. But if your degree of subcooling is very low, which is ideally in case of your dew harvesting, then probably your hydrophilic or a superhydrophilic surface would outperform a hydrophobic.
I have just one follow-up question. Actually, like most of the condensers, for example, power reactors, etc. Number one, they will have vacuum, and number two, they have to respect very strict water chemistry. So, do you see like does it require some more work, or is it like how do we overcome these difficulties?
Yes, I mean, of course, this does require more to be looked into in terms of water. The other aspect is using liquid infused surfaces. We are trying to use it in desalination plants, and desalination plants, as you rightly said, the water quality is of utmost importance more than anything else. And that is where the chemical analysis and these directions are kind of looking into. So yeah, therefore that is very pertinent depending on the particular application. Try to test these and see what the outcome is, be it in terms of pressure, be it in terms of let's say the contaminants that is going into the erosion that is happening. The other factor is when there is a drop or a loss in heat transfer, to what extent is the loss? Does it falls like right away, or is there a gradual decay? Because all of these things are very necessary in designing a system. And so therefore, based on the particular system, it would be relevant to investigate that particular direction.
This presentation. Some years ago, I did some experiments also with the RAS, and we obtained 130 degrees with excellent decay. So I mean, also other papers have shown. Shown that we can reach much higher contact angles. I was puzzled by the fact that you reach only 70 degrees or 60 degrees.
So yeah, so if we change, so I think that is also a function of the infusing lubricant. If the infusing fluorinated oil. Yeah, so depending on the working fluid as well as the fluorinated oil, it could also be based on the structure, and that can. So this is definitely not the highest limit. So that it can go larger, but this was easier to like scale in terms of fabricating an entire condenser based on a copper. And therefore we went with this, but definitely there can be surfaces which can go with higher power.
Okay, so let us give a round of applause.
Thank you, Dr. Soumyadip Sett, for your informative presentation. I request Dr. Susmita Das to present the moment.